Alright, in this video, we prove one of the practical foundations of Riemann integrals. That is, any continuous function on a closed interval is Riemann integrable. Okay, let's start. Let us first state the theorem. That is, a continuous function on a closed interval, let's say between a and b, is Riemann integrable. So we just say integrable to mean Riemann integrable. So the goal of this video is to prove this theorem. So here's the proof. First, let f of x be continuous function on this interval, closed interval. And as we know, any continuous function on a closed interval is also uniformly continuous. So thus, f of x is uniformly continuous. On the same interval. So what this means is, uniformly continuous means, for any epsilon positive, and there exists some delta such that for all x and y in this interval, if the distance between x and y is less than delta, then the distance between the difference between f of x and f of y is less than epsilon. But in this case, we use just, instead of just simple epsilon, we use epsilon over b minus a, because that will be more convenient for our purpose of proving the integrability of the function. To show the integrability of a function, we need to define the upper Riemann sum and the lower Riemann sum, and the limits of the sums should match. And to define those Riemann sums, we need to first partition the interval. Okay, so let delta be the partition. So a is equal to x0, and x1, x2, and so on, and xn, which is equal to b. And define, for each of the subintervals, we define mi to be the supremum of the functional value of x, where x is between xi and xi plus 1. Maybe we should put this equal sign here. And I is, between 0 and n minus 1. And lowercase mi to be the infimum of the functional value in the subinterval. And because the function is uniformly continuous, we have that the difference between this uppercase mi and lowercase mi is, look, this. So always less than epsilon over b minus a. So using these values, we can specify the Riemann sums. The upper Riemann sum, capital S delta, so delta is this partition, is given by I from 0 to n minus 1, and mi times xi plus 1 minus xi. So this is upper Riemann sum. And lowercase s delta is the lower Riemann sum. So defined by using this lowercase m and the length of the subinterval. So this is lower Riemann sum. Now we calculate the difference between these two sums. So capital S delta minus lowercase s delta So this one and this one, they are common factors, so we can factorize. So after factorization, we get large mi minus small mi times xi plus y and 1 and xi. Now, because of the uniform continuity, we have this inequality. So this sum is less than this and epsilon over b minus a, xi plus 1 xi. But this one is constant, so we can take it out of the summation. And we have this sum. But if we expand this summation, so we have x1 minus x0 plus x2 minus x1 and so on. So this x1 and this x1 cancels out, and this x2 will be also cancelled and so on. And in the end, we have xn minus 1. And this xn minus 1 will be cancelled to a previous one. So what's left is this one and this one. So we have epsilon b minus a, xn minus x0, but x0 is a, xn is b. So this one and this one, they cancel, and we have epsilon. So that means this difference is less than epsilon, but epsilon is any positive constant. So that means this will converge to 0 as we refine the partition, finer and finer. So in particular, we have infimum of capital S delta, infimum with respect to the partition, and supremum of lowercase delta, supremum with respect to this delta. So this is less than epsilon. So that means the infimum of the upper Riemann sum is equal to the supremum of the lower Riemann sum. So this equality indicates that the function f of x is integrable. And we are done. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.